Hi. Now this is in continuation to our previous video lecture where we were trying to understand that the change in the number of bond pairs and lone pairs will affect the shape of the molecules, right? And we took this example of molecules that have 3 electron pairs. First example we took of AB3 type molecule, right? Example was BF3 where we have 3 bond pairs. So when we have 3 bond pairs, the shape of the molecule was triangular planar, right? So when we replaced one bond pair with the lone pair and the molecule is of this type AB2L, right? Here the shape changed from triangular planar to your V-shaped or bend shaped, right? Now we will look at the molecules that have electron pair 4, right? They have 4 electron pairs, right? And why this change in shape? Change in shape is due to the repulsive force, the change in the repulsive force, right? Change in repulsive force will change the shape of the molecule, right? Because here we have now lone pair and there is force of repulsion is more between lone pair and bond pair, right? So these will move far apart, right? And will change triangular to a V-shaped, right? So now let's just look into the electron pairs that have the molecules that have 4 electron pairs, right? You can just take this down. I'm just rubbing it off. So the molecule that have 4 electron pairs, we will see if all 4 are bond pairs, what is the shape? When 3 are bond pairs, 1 is lone pair, then what is the shape? When we have 2 bond pairs, 2 lone pairs, then what is the shape? So basically what we are saying is how the shape of the molecule is changed by changing the number of lone pairs and bond pairs, right? So now electron pairs is 4, right? Bond pair and lone pair 4, 0, right? Molecule is geometry of this molecule would be shape, it would be like this, A, right, B, B, B and B, right? This molecule is of type AB4, right? Example is CH4 methane or SiF4, right? These are 2 examples. And geometry would be it would be tetrahedral in shape. It would be tetrahedral in shape, and these 4 molecules, right? 4 molecules that are bonded via bond pair. These 4 bond pairs will acquire or will occupy the 4 corners of a tetrahedron, right? These 4 bonded atoms or these 4 bond pairs will occupy the 4 corners of a tetrahedron, resulting into tetrahedral shape, right? Now let's see how this shape will change if I replace one bond pair with a lone pair, right? So here it would be 3 bond pair and 1 lone pair, right? So it would be somewhat like this. Right? Now what is changing? Lone pair is changed. So due to change in the electron pair from one bond pair to one lone pair, right? The force of repulsion, earlier there is force of repulsion due to bond pair and bond pair, right? There was no lone pair, right? And we have seen that the order was this: lone pair was greater than lone pair, bond pair which is greater than bond pair, right? So we have maximum repulsive force between lone pair and minimum between bond pair. So here the repulsive force was minimum due to bond pairs, right? So when I changed when I replaced one bond pair with a lone pair of electrons, we know that this lone pair of electron will occupy more space because its electron cloud is more, since it is localized on one central atom, on this single atom, right, whereas these bond pairs belong to 2 atoms, right? So the force of repulsion, if you look at this range, if you look at this sequence, I'm sorry, the force of repulsion between lone pair and bond pair is less than lone pair, but more than bond pair, right? So this force of repulsion, right, by replacing this shared pair with a lone pair has increased. So force of repulsion has increased, so this will change the shape of the molecule. This shape, the molecule is of this type, AB3L, right? Now the shape of this molecule would be trigonal pyramidal, right? The shape is the geometry, what we call it, this would be trigonal pyramidal. This is the shape of the molecule, right? An example of these shapes would be PCl3, NH3, right? Example would be PCl3, right? NH3, right? These are the shapes. We will be looking into these shapes in future lectures in detail, right? Now suppose here we have only one lone pair, right? Now if I replace one more shared this bond pair, right, with a lone pair, right? Now the shape of the molecule will again change. Now we have two lone pairs, right, and one bond pair, and molecule will change like this, AB2L2, right? Now again the shape of the molecule will change, right? Now just try to understand why the shape is changing. It's because of the change in the repulsive force, right? Earlier the repulsive force was between lone pair and bond pair, right? Earlier the molecule was like this, it was A, right, bond here, right? So this was lone pair, this was bond pair, this was bond pair. So force of repulsion was between lone pair and bond pair, and here now there is one more force of repulsion, lone pair and lone pair, right? The shape is here, it is between lone pair and lone pair. Now here it is between lone pair and bond pair, and here also you have lone pair and bond pair, right? So here now, due to the presence of two lone pairs, we have lone pair repulsion, and we know that lone pair repulsion is maximum. Since the lone pair repulsion is maximum, now again this electron pair will take a different position, right? Because if you remember, we said that these electron pairs will take definite positions, due to which molecules have definite shape and geometry, right? In this case, the repulsive force was different, so the position occupied by these bond pairs is different. When one lone pair was introduced, repulsive forces has again changed, so the position occupied by these lone pairs and bond pairs will again change, right, resulting into trigonal pyramidal. Now instead of one lone pair, I have two lone pairs, right? Now due to the presence of two lone pairs, we know that the electron cloud of lone pairs is bigger, right? It occupies more space. More space means more repulsive force, right? So we have more repulsive force between these two lone pairs, right? So they will, now these lone pairs, due to high repulsion between lone pair will take a different position. When they will take a different position, their shape will again change, right? So from trigonal pyramidal, it will change to a V-shaped or a bent. It will change into a bent molecule, right? So just try to understand, it's the repulsive forces that are acting here, right, due to which the shape of the molecule is changing, right? Now example is NH2 molecule. For this it's NH2 minus. This molecule or this ion has this V-shaped, right? It has two lone pairs, and there is one more molecule, it's water molecule, right? We will look into the water molecule in detail, right? Water molecule also has bent shape. It has oxygen atom, has two lone pairs, right? And these two hydrogen atoms are connected to it via two bond pairs. So this molecule is of this type, AB2L2. it has V-shaped molecule, right? So I hope this is clear. Now we will take another example where the electron pairs will change from 4 to 5, right? Now electron pair will change from 4 to 5. Let's just rub this. You can just take these down, take down these notes, and make sure you understand the repulsive force, right, and how the repulsion increases or decreases, right, by varying the bond pairs and lone pairs, right? So when the repulsive force will change, these electron pairs, which are lone pair and bond pair, will take different positions, right? So when they take different positions, their shape will change. Remember this point, right? Now electron pairs 5, right? So bond pair, lone pair, let's say 5 0, right? And the molecule is of type, it would be the AB5, molecules would be of type AB5. Example is your PCl5, phosphorus pentachloride, right? So it would be A molecule, this is how we draw it. This is your bond pair again. Right, this is how it looks like, right? So here we have all these are bond pair AB5 type molecule, right? So we'll just see how the presence of more lone pairs will affect the shape of the molecule, right? So this molecule is of type, this type, right? Remember, or just notice, all these are shared pair, bond pair of electrons, right? So here the shape is pyramidal. I'm sorry, the shape is trigonal pyramidal. Example is PCl5. Shape is trigonal pyramidal, right? Now if I replace one bond pair with a lone pair, right? If I replace any of these, this molecule is of AB5 type, where we have 5 bond pairs, right? Here we have bond pair, here we have bond pair, right? Here we have bond pair, here we have now lone pair, right? I replaced one bond pair with a lone pair, right? Now here the repulsive force was between all the bond pair of electrons, right? All of a sudden now there is one lone pair. Now the force of repulsion, if you look here, is more between the lone pair and bond pair, right? So due to this force of repulsion, which is high compared to bond pair, these lone pair and bond pair, this and this, will take a different position around this central atom, right? These lone pair and bond pair, due to difference in repulsive forces, will take different positions around the central atom. That will change the shape of this molecule, right? So it will change the shape of the molecule from trigonal pyramidal to a seesaw, right? The shape is seesaw. The shape of the molecule is seesaw. An example is SF4, right? Example of is SF4. This is how this molecule looks like. Right? Shape is seesaw. SF4 example. Now let's do one thing. Let's replace one more lone pair. One more bond pair with a lone pair. Right? Let's see how the shape of the molecule will change. Now it would be somewhat like this. this is your bond pair, this is your bond pair, right, and this is your bond pair, this is your lone pair, and this is your lone pair, right. Now earlier the force of repulsion, right, was between lone pair. Here we have the force of repulsion lone pair bond pair and bond pair bond pair. Two types of repulsive forces were acting, lone pair bond pair, bond pair bond pair. Here now if you see the repulsive force here, this is between bond pair lone pair, this is bond pair lone pair, and this is bond pair bond pair, and this is your lone pair lone pair, which is maximum, right. Since again repulsive forces have changed, right, a more high repulsive force has resulted due to the presence of two lone pairs. So again these lone pairs will take different positions based on this point, right. That will again change the shape of this molecule. It will change the shape of this molecule to T-shaped, right. Now the shape of this molecule is this would be T-shaped, right. Now if you take another example, here you have two lone pairs. Now this molecule is of type AB3L2, right. Now if I take three lone pairs, right, here two lone pairs, now we have three lone pairs. Now repulsive forces will again change. Here the molecule was facing repulsive force here in this direction between this bond pair and this lone pair. Now repulsive force is from this side also. High repulsive force which is between lone pair and bond pair is from this side also, right. So now the shape of the molecule will change to linear, right. Shape of the molecule will become linear. An example is XeF2 molecule, right. So now we are clear how changing the number of bond pair and lone pairs around the central atom will affect the geometry of the molecules, right. Basically why? Because if you change the number of lone pair and bond pairs, the repulsive forces will also change, right, based on this. So more is the repulsive force, or if the repulsive force will change, the bond pair and lone pairs, right, will take different positions, right, so as to have minimum energy and maximum stability. They will try to move as far apart from one another, thereby acquiring different shapes, right. So that is why we say based on the number of electron pairs, bond pairs or lone pairs, the shape of the molecule is decided, because changing the lone pair and bond pairs will change the repulsive force, that will change the shape of the molecule, right. Now we will go the other way around, right. If you are given, suppose you are given the molecule, right, and you are asked what is the shape of the molecule. How will you find the shape of the molecule? You need to know the shape of the molecule, we need to know the lone pair, the bond pairs, right, around the central atom. Once you know the lone pair and bond pair around the central atom, you will know the shape of the molecule, right. So here the question that you get mainly is, based on VSEPR theory, right, predict the shape of the molecules. Predict the shape of molecules, right, based on VSEPR theory. So what you need to know is, you need to calculate the number of electron pair, bond pair and lone pairs, right. If you want to know the shape of the molecule, right, you need to know the bond pair and lone pairs, right. So calculate the number of lone pair and bond pair of electrons right? Now let's see how we will calculate the number of lone pair and bond pair. Suppose you are given a molecule ClF3, right, ClF3, and you are asked to predict the shape of this molecule based on VSEPR theory. So you need to find the number of lone pair and bond pair, right? So the number of electron pairs, first you need to know the number of electron pairs, right? Once you know the electron pairs, these bond pairs are equal to the number of bonds, right? Bond pairs is equal to the number of bonds in the molecule, right? So number of electron pairs would be, there is a formula, half number of valence electrons of central atom plus number of atoms linked to the central atom. Number of electron pairs, the number of valence electrons, around central atom plus number of bond pairs, right, or the number of atoms linked, right, to the central atom, right, number of atoms linked to central atom by single bonds, right. Using this you will find the number of electron pairs, right. So once you have the electron pairs, you will see how many atoms are linked to the central atom via single bonds. Once you know the number of single bonds, you will find the number of bond pairs, right. So then you subtract the bond pairs from the total electron pairs, that will give you lone pairs. So you have lone pairs, bond pairs. You can predict the shape of the molecule based on whether the molecule is AB2L type, AB5 type, the one that we have done just a while ago, right. So if in this case we find the electron pairs, it would be half number of valence electrons around the central atom. This molecule would be like this, right. So chlorine has 7 valence electrons, right, number of valence electrons around central atom. This is the central atom. We know chlorine has 7 valence electrons plus number of atoms linked to central atom by single bonds. In this molecule, 3 atoms are linked to this central atom via single bonds, right. So this would be 10 upon divided by 2, it would be 5. So we have 5 electron pairs, right. We have 5 electron pairs, right. This we know now, this number electron pairs. Now we need to find the bond pair and lone pair. Bond pair is, how to find the bond pair? Bond pair is equal to number of bond pair is basically the number of these single bonds, right. This is your bond pair, right. So number of bond pairs, number of atoms linked to central atom, this is the central atom. Bond pairs would be number of atoms linked to central atom by single bonds, right, by single bond. How many atoms are linked via single bonds? 3. So bond pairs are 3. So what would be lone pairs? Lone pair would be, total would be is 5 minus 3, 2 lone pairs, right. So this molecule is of type AB3L2, right, and we have done the bond pair where bond pairs were 5. If we have 2 lone pairs, right, this is AB3L2 type, this is your T-shaped molecule, right. You have to remember the previous chart that we have done based on the number of lone pairs and bond pairs, what is the shape of the molecule, right. And if you draw it, it would be like this, B, 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 lone pair, lone pair. So here you have maximum repulsion, here you have repulsion. The shape of the molecule would be T-shaped. So this molecule is your T-shaped, right? I hope this is clear. You just need to, in order to find the shape of any molecule, you will find you need to know the number of electrons around the central metal atom, right? Plus the number of atoms linked to central atom by single bonds. Here we have 3, right? 3 atoms linked by single bonds. So half 7 plus 3, 7 is the number of valence electrons around chlorine, 3 are the number of atoms linked to central atom via these single bonds, right? So number of electron pairs are 5. So in order to know the shape of the molecule, we need to know the number of bond pairs and lone pairs, right? So bond pairs would be the number of bonds. Bond pair is basically the number of shared pair or the number of bonds. We have 3 bonds, right? So we have the bond pairs are 3. Bond pair is number of atoms linked to central atom by single bonds, 3, right? So lone pairs would be total electron pairs minus bond pair, it would be 2, right? So molecule is of this type, it is T-shaped, right? I hope this is clear. Now let's quickly see another example so that it would be clear to you. Let's quickly take another molecule and try to find the number of bond pair and lone pairs. Once you know the number of bond pairs and lone pairs, you will know the shape of the molecule, right? The molecule is H3O, right? So in this case, in case of positive ions, right, you need to subtract the electrons equal to the positive charge, right, from the valence electrons of the central atom. Here the central atom is oxygen, right? It would be like this, right? We have 1 positive charge, so we will subtract this 1 from the number of valence electrons of the central atom. For all positive ions, we would be following this, right? For all positive ions, we will subtract the number of positive charge from the number of valence electrons of the central metal atom, right? So it would be number of valence electrons, number of valence electrons around. So in this molecule, how many valence electrons would be around oxygen atom? Plus means electrons have been lost, right? This we know. Cations are positive ions, that means they have lost the electron. Here plus means they have lost the electron, so we need to subtract the number of electrons lost from the total number of valence electrons that are in the valence shell. Number of electrons around oxygen, which is the central metal atom. Normally the number of valence electron is 6 minus 1 positive charge. This is your 5, right? So this is the number of valence electrons around the central atom. Now you can apply the formula half to know the electron pairs, right? To know the electron pairs, half number of electrons around the central atom plus number of atoms linked to central atom by single bonds, 3, right? It would be 8 upon 2 equal to 4 electron pairs, right? We have total number of 4 electron pairs, right? So number of bond pairs how much? Equal to the number of single bonds, right, or number of atoms linked to central atom by single bonds. It would be 3. So number of lone pairs would be EP minus BP would be 4 minus 3, it would be 1. So molecule is of type AB3L1, right? This is the type of molecule AB3L1, right? So this is your trigonal pyramidal. If you look at the previous, it is trigonal pyramidal. The shape of this type of molecule AB3L1 is trigonal pyramidal, right? So you can practice some more examples. I hope all this is clear. Thanks.